Okay, so we are going to start today. We'll talk about very important method which is called BagofWords or BagofFeatures. Last few years this has really attracted a lot of attention in the community, and it really works very well. And this is same approach works for the images. It works for also video. In images, we look at the different objects like chairs, bicycles, and people. In the videos, we look at actions, the human activities, running, walking, and jumping, and so on. So these are the slides I got from Cordelia Schmidt. She's a pretty famous researcher in France, India, and I have modified some of them, so I want to give her credit. So the contents are that we will go through interest point detector, which is like SIFT or Harris, which you have implemented, and then around interest point descriptor like HOG or the SIFT descriptor. Then we are going to talk about new concept called Kmeans clustering. So we'll take a bunch of points and cluster them automatically. We already talked about clustering using the mean shift. And then we will also talk about very briefly about very important technique called support vector machines classifier, or SVM, which is another thing last 10 years or so. We have really revolutionized the field of computer vision, machine learning, and so on, and almost everybody is using SVM. So it is important for you guys to get a insight about what SVM does and how you can use it. Of course, there's a whole course on these machine learning one can take. There are a lot of good online lectures also. Okay, so the last topic will be that we'll talk about how can you evaluate the methods which will do the image classification or object classification and action recognition and so on. So in particular, we'll talk about precision recall. Okay, so let's get started. We have an image classification problem like this. We have an image, and we want to assign a class label to this image. So we want to say, in this image is car present, cow is present, bike is not present, horse is not present. These are the classes: car, cow, bike, horse, and there can be several other classes. Okay. So other way will be, which will be much more finer, that we can localize these objects also. So while car is there, the bounding box which is on the left side, and there's a cow on the right side, and we have a location and also category. That's what we want to do. So now it is a difficult problem because of these factors. Like if you take a picture of this person from different viewpoints, the picture may look different. If you take a picture in a different illumination, it may also vary, as we have talked about face recognition. And these objects may look different even in the same class. So therefore we will have lots of these set of images, and we want to use them to come up with some method which can deal with these different variations. Okay, so let's take an example of a chair. Now these all are chairs, and you see that within a chair class there's a lot of variations, and that is the problem. Okay, so this is called intra-class variation. Inter-class will be that variation between chair and a motorbike, for example. So then image classification is given positive trending images. In this case, the object is motorbike. There are several images, and these images contain the motorbike, and also several negative images that don't contain this particular object. These are the images like airplane and so on. So we want to classify a test image as to whether it contains that object class or not. So we are given a test image. We want to say, does it contain the object or not? So this is a learning-based method that we learn what the motorbike looks like. What are the features which motorbike image will have, and there'll be testing. So there are these two parts, learning and testing. So you need to understand that. Okay. So we are going to use this method called BagofFeatures, or the histogram of features or distribution of features. As we were talking about yesterday, the distribution is like a histogram. So distribution, you count how many number of times particular feature occur. You can get a histogram of an image where you have 0 to 255 levels, and you get a histogram, say, well, in this image the pixels which has gray level 50 are 100, the pixels which have gray level 200 are 30, and so on. That's a distribution of the gray level. It's called histogram, and it is also called a bag. That we have these big bins, 250 bin or 256 bins, and we have this, we want to represent that. So like that, we will have a bag of features, or histogram of feature, and this idea comes from the texture recognition. So if you look at this image, there's a repetition of these primitives. Most of the time it's repeated this kind of circle which is filled. This is repetition, is a texture image. Okay. Now in this one we can identify maybe there's one, and maybe if you go to a little higher level, maybe we'll have this kind of primitive and this kind of primitive. So these primitives can define this whole texture, and we will look at the distribution of this image in terms of these primitives. Okay, so this is another texture. This is a little different, which is denser. Here may be these primitives. These primitives are texture element, like you have pixels, picture element, or these are also called texton. Okay, so this is a third example. These can be a texture element, and we can define these images in terms of distribution of these texture element. So let's say we have this image, and these are the texton. These are the texture elements. And then we can represent the histogram of these for this image. And so this reduces the dimensionality, that we'll have just one vector which will represent this image, and which is important. And this may have these texture element, and we will have histogram of this image like that in the third example. Okay, so that's a basic concept which you need to be clear about. So now this is also similar to the documents. When you look at a document, like a Word document or document on the web page, it consists of lots of words. Okay, so words are the elements, basic elements in a document, and you can come up with representation of a document as a bag of words or a histogram of words. Okay, so there's no order. You say, well, how many times in this document this kind of word occur, like a bank, loan, water, farmer. So these are the 4 words. We take an example and look at each document. In this document, this word occurred once, this occurred once, and this does not occur, this does not occur. Second document, this occurs once, this word occurred twice, and so on. So this is in a way a distribution of the words for this document, and similarly we have distribution of other documents in terms of these words, and we can normalize them, and we can get basically a probability or distribution which is like that. So this is also called bag of words, because here we have words as a unit, like we have a text on there. Here we have words. These are documents, not images, and this is called bag of words approach. And this is used a lot when you want to match 2 documents. Okay, you get a histogram of words, and you do the intersection. That how similar these documents are, you say they are the same. If they are very different, then the histogram intersection will be small. So that's very easy way to look at the millions of documents on the web to find out quickly which document matches the best. Okay, so therefore we can apply the same idea to images. Of course, for documents it's easy because we know the English language, we have a vocabulary, we know the words. But now, what are the words in the images? So these are the images. Okay. Now words, are in terms of little picture element, little pages and so on. There's no English word there. So what we are going to do, that we will actually detect the features in the image, and these will be your Harris corners or shift points, and around each we will get a little patch, okay? And then we will local patches as shown here, and then we will compute some descriptor for each of the patch as you have done, like HOG, like a shift and so on. So these will become vectors, the descriptor for each of this. So now we have these lot of these vectors, and we are going to do the clustering of those. And this typically will be shift will be say 128 dimensional feature vector, and the HOG will be about 3000 dimensional feature vector and so on. But just an example, let's say these are 2-dimensional, just to demonstrate. So each of this page or vector will map it somewhere here. So these are different, pages, and then we want to cluster them. Say, well, these are very similar, so this can be one cluster, this can be another cluster, and so on. And then we will call each cluster as a word. So this is a word, not an English language, it's a word for the image, in terms of the feature vectors, which are the descriptor around the interest points, and that's the way we can represent the image as a bag of words, or they are also called bag of visual words, not the words in documents. Okay, so that's the idea. So therefore, we'll take image like this. We will get these get pages, and then we will get these words from these images, and then now we can represent an image in terms of a histogram of these words. And so it's now similar that we are representing the document in terms of histogram of words, which is very nice, and actually it works very well. There's a whole set of papers, people are doing that, and it really is a big change in computer vision that people started doing that for last 5, 6, 8 years ago. Okay, so this is also called bag of words, bag of features. So you need to kind of understand these different terminology, and bag of visual words. So the same thing. So another example from here. Now you have to understand that whenever we find a histogram, you lose the order. The histogram does not have any order. So I can take an image half black and half white. I can take another image where you have checkerboard, alternate black white. Histogram of both of them exactly same, because counting number of pixels, what gray levels they have. So histogram does not carry any spatial information. It does not have any order. It's a distribution. Okay, so therefore this when you find a histogram of words, it is orderless. It does not tell you, say, these words occur in which order. Doesn't care. It say how many times this word occur in this document. We don't care where it occurs. Does it occur or not? Okay, so therefore that's important point. And so we can classify documents. Another example here, we have 4 documents. As you see, the words are common, people, common, people, and sculpture, and all this thing. And then we can come up with this representation of bag of words. For the first document, common occur twice, people occur 3 times, occur 0, and second one like this. So this is a distribution of these documents, is a vector, so which is very nice. So then the process for the images is similar, that we take an input image, we find some interest points, then we compute some descriptor, and then we find the clusters of those descriptors, as I explained to you, and then we have another image, we do the same thing, and then we train a classifier. That, well, these are the examples we have for this class, and we want to learn a classifier, and that's called support vector machine. So we learn that, then testing, we will give it an image, we compute interest points, we compute descriptor, and say, is it a positive or negative class? Then that's it. So that is the way you can basically detect or recognize a object or classify an image. Is this image of a person? Is it image of a bicycle? Is it image of a motorbike, or any other category as you wish, as far as you have learned those categories and you have training examples of those. The training example has to be positive and also negative. Okay? Okay, so now the first step is detect interest points, and you have a program to detect shift or the Harris, very easy. Then if you don't want to do it, as I said, just take every 5th or every 10th pixel as your interest points, which is called dense sampling, which actually works very well. You can save computation. And then for each interest point, compute a descriptor, which you know, HOG or shift. So you are done. Then, so these are dense features. You take an image, you say, well, every 5th pixel, you take a window, that's my interest point, this interest point, all these, that's it. And it actually works better than the Harris detector and then find interest, the descriptor of that. So that's what we have. Now, as I explained to you before, we will have a descriptor for each interest point, and it will be in high dimensional space, and we want to then cluster them to come up with the words, and that will be our vocabulary. But the English language has vocabulary for thousands of years ago. But visual words, we don't have vocabulary, so we have to come up with our own vocabulary. So this is an example again that we have, say, 3-dimensional space, and we have these different descriptors from these different images. We want to cluster them, and we may come up with one cluster here, another cluster here, third cluster here, and these will become word 1, word 2, word 3. Okay? So now how do we do clustering? So we have, say, lots of vectors, okay? And we want to cluster them. So the most simple method to clustering is called Kmeans. Okay, means mean mean, sample mean. K means how many clusters you have. Suppose you have 3 clusters, you can find those clusters, or 5 clusters, and so on. So that's the very simple intuitive method, and it actually works pretty well. So once we do the clustering, then each cluster will become word. Then we will find the histogram of an image in terms of those words. Then we have vector. We can train SVM. That's it. Okay? So let's look a little bit about K-means. So let's say we want to do 3 means, which means we want to get 3 clusters. So we have, let's say our data is 2-dimensional. Again, it's very easy to understand when you have 2-dimensional, but it works for the 1000-dimension also. Okay? So let's say we have, these are the data points, which are saying dots. There are lots of them. It's not very obvious that, what these clusters are. And right now, ignore these lines, just look at these just points. So the K-means, the way this starts, that if you know that we have 3 clusters, you randomly pick 3 data points and assign them as the center of the cluster number 1, cluster number 2, cluster number 3. Okay? So we picked randomly 3 points. This is center of first cluster, this is center of second cluster, third cluster, and this is shown in yellow. Then what we are going to do, that the rest of the points we have, we want to assign to one of these 3 cluster centers, which are the yellow. Whichever this point is closest, it will be assigned to that. So this will be assigned to that, will be assigned to that, maybe this will be assigned to this, and so on. Then this will be assigned to that, and so on. So now at the end of this, we will have all the points assigned to one of those yellow circles. So that means that initially we will get this kind of boundary. This will be one cluster, and this will be another cluster. This will be a third cluster. Okay? So that is way we are going to do. And then because we assign these points to one of these clusters, now we can recompute the mean for each of those points which we'll assign. Okay? Because initially means were randomly, we just picked, say, well, this is the center of first cluster, this is second and third. Now we have assigned to these which are closest to one. So we'll use all those points to find the new mean. All the points assigned to first cluster, we'll take them and find the mean. All the points assigned to second cluster, we'll find the mean. All the points assigned to third cluster, we'll find the mean. And then second iteration, the mean will be like this for the first one, for the second one like this, third one like that. So then the division will be like that, the second one. So all these points will be first cluster, all these points second cluster, all these third. Then we'll keep repeating, we'll do the third iteration. And this mean will become like this. So then we will have one division like here, all these points, one, another one, another one. So that's called K-means algorithm. So every time we want to update the mean, and we know there are K-means, that's why it's called K-means. In this case we know 3 means, and we're just doing that. Pretty simple, iterative, but it really works. Okay, there are lots of methods which are more complicated, maybe they will work a little better, but this is pretty very intuitive. So the algorithm is, we have the data points, we choose K data points to act as cluster center, as I explained to you, and we'll repeat this until clusters are not changed. If you keep repeating, nothing change, then we stop. Then allocate each data point to cluster those that is closest to, nearest to. Replace the cluster center with the mean of the elements in their clusters, because now we have assigned these. Keep repeating, keep repeating. That's it. 2 lines of code, you're done. Okay? That's your K-means. So if you do that, then these will be the visual words you can get from the examples of, say, airplanes. Maybe you will get a fuselage, maybe, wings and so on, motorbikes. These are the little words. Faces, maybe you can get eyes, a hair, and leaves, you can get part of leaf. People, you can get maybe faces. Bikes, you can maybe get tires and so on. I mean, this is what you are trying to do. Ideally, maybe not all of this will happen, but that's the idea, that you want to represent the image in terms of these local pages, and each is like a visual words. So this corresponds to like a document. And this is obtained, this is the cluster center of those descriptors we got. So we have interest point, we got descriptors, we have a lot of training examples, and then we cluster them. Each cluster center is a word, and this is the representation of that. Okay? So that's the idea. So then at the end, we can take this car image and represent as histogram that. The bag of words, representation of a car, and we came up with our own vocabulary. So this is similar to the bag of word representation of a document in the English language. The words, they are given there. Shakespeare had the words, so we didn't have to invent the words. And here we have images. What are the words? And we have one way to find those words. To detect interest point, get the descriptor, cluster them, each cluster is a word. It's very nice. So this is your representation, okay? So then each image will be represented by 1,000 or 4,000 dimension vector, and then we are going to do now SVM, the learning. So we are going to learn a classifier, and that essentially will learn a decision, a rule, which will take. Yeah, sorry.
I just have a question.
Yeah.
When considering that you're actually doing the actual interest points based upon not taking into consideration geometry of pictures, how well does that actually classify in practice versus if you were to design features specifically considering geometry?
Yeah, that's a very, very good question, and very nice. It's important. So see I'll show you the results. So in terms of working, the accuracy, the precision, recall, it works very well. But in terms of understanding that while the system recognizes as a bike or an airplane, there's a problem, because you may get the words which are not that meaningful. but it, you cluster them, because see that when you are clustering, when you are detecting interest point, we don't have any notion of this should be a tire, this should be a fuselage, this should be an eye or face, no notion, which is a interest points. So we take those interest points, we do the clustering, we don't know anything, it just cluster. So then some of them are meaningful, not all of them are meaningful. So that is a serious problem, and there's a whole research people are doing on that. Yes.
So would that be useful in something like close estimation?
Yeah, that's right. Yeah. So you won't be able to localize, for example, that easily, because you're taking an image, you're finding histogram, you say, well, is it a bike image, is it an airplane, is it a human image? That's it. So that's a problem. But this is the beginning. We just want to classify. We have a web image, billions of images. We say, well, separate the car images from the bike images, and we can do that. So that's the idea. Okay, so we want to come up with a decision rule, which will assign BagofFeature representative image to different classes, and this is again very intuitive. Okay, so we have we have a zebra image like that, which is shown green, and then we have these other images. They are not zebra. So we want to separate the positive example from negative. In this case, we want to classify a zebra. So the green one is positive and red one are not. So whenever we want to learn, it requires a data, a training data. So we will take the positive examples of this, like a motorbike. We will find this representation as a histogram with a bag of words. There's one vector for each example. And then we will have negative examples which are not bike, like that. And then we want to classify them. We want to learn the classifier. Support vector machine, SVM. This is one thing which has impacted a lot. Machine learning, computer vision, many other areas, and it is a very powerful tool and works very well. And I'm going to tell you where you can get a code which you can use it. Okay, and it will be very superficial, very high level description to just give you a flavor of what is support vector machine. Again, there's a whole course on machine learning where they cover this in detail, and there's actually very nice YouTube video on this also if you want to learn more about it. There's a professor in Caltech, he has a very good course, and he has a very good lecture on this also. Okay, so first is, we need a classifier, it's recognized, it's used for, pattern recognition, we recognize patterns, object classification, detection, and so you want to train a classifier using a set of positive and negative examples, and then classifier will learn the regularities in the data, that while all these are, say, motorbike and these are not motorbike, it will separate them. And if the training is successful, then we can take an image which the classifier hasn't seen. It should be able to tell you this is the bike and this is not the bike. That's called testing. And that's what we want to know, because ultimately computers need to do which like humans can do. It doesn't need, like, we'll have some training example. We know humans say, well, these are all the bike images. We know these are not bike images. We'll use them. They are labeled for training. But once we are done training, the testing has to be blindly, that we give an image and it has to tell us it's the motorbike or not. Okay, that's the whole idea. So the this classifier, first is this will be a binary classifier. We'll just say motorbike or not motorbike, human or not human. Two classes, positive, negative decision. Once you understand that, then you can easily extend this multiple classes, which is very easy. Okay. So let's say we have two examples, positives and negative, the red and the blue one, like that. And each one is example, again, it's in the feature space. We have two-dimensional feature here. In your case, it'll be 1,000 dimensions or something, but it's the same thing. So the first example, feature is like here, this feature, this has two-dimensional feature like that, and so on. So what we want to do, given these examples, we want to find the boundary. We want to find the line, equation of a straight line. Y is equal to mx plus c in the plane, in this 2D case. In the multi-dimensional case, we want to come up with a plane, hyperplane, which will cut these two classes. Okay? So then if we can find this line, then it's very easy because this line separates these two classes. And if we go on this side, because here it is equal to 0, W3x plus b is equal to 0. This is the equation of line here. If we go here, this will be greater than 0 for all these examples. If we go here, this for all these examples will be less than 0. If you are on the line 0, if you are on the left side of the line, it is positive. If you are on the right side of the line, it's a negative. That's what we have. So therefore, classification will become very trivial once we know the line. What we are going to do, take the unknown example, plug in this equation, look at the sign. Okay? So if the sign is positive, then this class, if it is negative, this class. That's it. Yes?
What are the variables?
The variables are variables of the straight line. So we have straight line equation y is equal to mx plus c. So given these points, we want to find that line, and then we will have the equation of a line, which will be y is equal to mx plus c. Now here we will have the particular example which will be given x and y, because it's a two-dimensional vector. So we take x and y, two-dimensional vector, put in that equation, we look at the sign, y is equal to mx plus c. So the variables we have to compute whenever we want to fit a line is m and c. So we'll compute the line using these training examples, that what's the line which separates these two. Once we know the m and c, then we can take any xy, plug in, find its sign, positive, negative, or 0. Okay? So now, depending on how these positive and negative examples are, it will become to get a really good line separating them automatically. I mean, we're going to compute a program to get the line, right line, because they may be very nasty, be a problem. So that is what, there are possible lots of lines. Okay, so now which line to pick and which is the best line and so on. There's a whole issue there. So there is this notion of margin, which is the distance of a point from the line. Okay, so that you can find out like this. So now the distance, this is the closest point in this class to the line. This is another closest point on this class, and so on. So we can find these distances. This is further away. Okay? So in general, to separate these two classes, we want to have some margin. More margin it is, better it is. We won't get confused. Okay? So this essentially is the margin. Okay? So now we want to find this line such that this is margin, which means we want to find these vectors, which are actually examples from the red class, and these are examples from the blue class. One is a positive, one is a negative. So if we know these vectors which are on this margin, these vectors which support these lines of the margin, and these vectors are called support vectors. That's why this method is called support vector machine, SVM. So this classifier means you just have to find those vectors. That's it. If you can find these vectors, in this case these 3 vectors, 2 from here, 3 from here. You don't need all these examples. That's it. You don't need those examples. You just find those 3 vectors that define the classifier. That's why it is actually better than finding the lines. It is better than looking at all these data. Just find the support vectors. And it is called support vector machine because these vectors support these lines which are the margin. Okay? That's it. So you are given these red dots, blue dots. This is like a Democrat and Republican, and select the ones which support this country, So you have to get, both of those guys. Okay, so that's it. So you want to find these examples in hyperplane which are support vectors so that this margin is maximized, and this support vector machine will do that for you. So of course, there's a whole optimization problem. How you find those? There's a convex optimization. There's a program and so on. It's pretty involved mathematically, and you can learn that, in the machine learning class. But this is the code. You get a code from there, and it really works. Everybody uses. It's called LibSVM, and that has really a big impact on computer vision, object recognition, action recognition, in many areas. It's a very simple, notion that how you can, describe a classifier in terms of these support vectors and how you automatically find these support vectors. And there's lots of interesting things here. Now here you see that these are linear. It's very nice. You can find boundary. But in cases that these boundaries are not linear, they are very, very difficult, space. This SVM can do that also using the kernel trick, that you do the transformation to different domain and you can take the nonlinear boundaries to linear boundary, which is another very interesting piece of work, and that will reduce to the distance, as you are asking. So if you find the Euclidean distance, you will not be able to deal with the nonlinear boundary curves. But if you use other distance, like a radial basis function and so on, then it actually will take care of also nonlinear boundaries. So it's a pretty interesting stuff, and it's very useful. It really works. Okay, so I think then we are done. So we have all the pieces. We have the words, which we got from interest binary descriptor. We did the clustering, and these are the words. Then we know how to train SVM. Now we can recognize the class. So it actually gave pretty good results, even in presence of background. So these are the different classes: bikes, books, buildings, cars, people, phones, trees. And so what you will have, you will take lots of examples of bikes, some variations. As you see, there's variations. It's good to have many different diverse examples. Go through the process, train us SVM for this, train SVM for books and buildings and all this thing. Then you can test them. So sometime it will have these problems with the books. It may get confused, maybe faces in buildings, and these are building images, trees and so on, where they're very similar, and then misclassified into buildings, phones, and something else. So it has problem depending on the data and so on. So now we want to talk about how do we evaluate how well you are doing, how well you are classifying. Okay, and there's a whole competition called Pascal Competition, visual object classification. Started in 2007, and it's done by European community. So they have actually caught these training data and test data. They went to the online, and then they distribute these to different teams, and they got images from, say, Flickr, and there were 500,000 images, and then they have 20 classes, 20 different classes, so the bike, horse, person, and so on. You can get these. It's freely available. And then they also have some annotations, like they know where is this particular object, bounding box and so on. And then they have training images, they have testing images, and so on. So now these are the typical, this is 2007. This started 2007 actually. They are continuing every year. There was one 2012 also in the conference I went to in Florence. So these are the example of airplane, bicycle, bird, those can cow, I'm sorry, and the chair, so on. There are 5 of those, 10, 5 on the top, 5 on the bottom, and there are another 10 here, dog, house, dining table, sofa, and so on. So it's pretty interesting, and if you are interested, you can actually compete next year in this. So now we want to talk about how do we evaluate how well a method works, because people will take this data set and they will have different variations of these methods. Then these people who organize this will evaluate each submission. So they may have 40 submissions. So they want to say who's the best one. Then they have workshop, and they invite those people who, top 3. They make a presentation. They talk about their method and so on. So it's a pretty interesting, process. So we want to talk about the basics. What are the evaluation metrics? Now, you can only evaluate if you know the ground truth. So you have 20 categories, so you have to have a ground truth that for each category you may have some images, say 50 images, and this is a dog and this is a person and so on. So you have ground truth, that's called ground truth. Then you want to look at what the output of the method gives you. Say there were 50 images, the submission 1, 50 images of a dog, submission 1, say from those 50, 30 are dog, but the remaining 20 say that it's not dog. So those 30 will be called the true positive, because algorithms say they are dog, and the ground truth says dog. And that 20 which it did not recognize, they will become true negative, because they were negative for this particular method. So therefore we have to look at these different terminology to kind of come up with a metric. So this is one slide, but this is very important, so you want to listen very carefully to that. Okay, so let's say we have a red circle. It is all the ground truth, and all the examples in that are the true class, say for example all are dog. Then the blue circle is the examples which your algorithm say they are of that class. Let's say dog. So the blue one are the results of your method, and this is a ground truth. So you see there's intersection, and lots of them are common, which is good. And these whenever you want to test a classifier, then you need to have also example from other class. Not only it should say dog is dog, but it should say cat is not a dog. Yes? And those cat in the scale will be true negatives. Okay? So you have ground truth, you have result of your method, and you have two negatives. Now the intersection of the red and the blue one are true positives. because these were the ground truth and these were also your algorithm. It's told you they are correct, which is good. And in general, we want to optimize that. We want to maximize that. Okay? So then, now these examples, the algorithms say they are dog, but they are not dog. So they are false positives. Okay? Because they were something else. So those one are false positive. Then we want to look at, it missed these. It says these ones, with the ground truth say they are dog, but it says they are not dog. That they are not in the blue one. So those will be called the false negatives. Okay? So using these definitions, now we want to come up with what is called precision. So precision is this intersection between the ground truth and your algorithm, this whole area, divided by divided by your blue circle. So that is the intersection of ground truth, your RM, which is the result of your algorithm, divided by your output of your algorithm, which is RM. And which essentially is true positive, because this intersection is true positive, divided by your algorithm, whatever it gave you. Then it tells you how precise your classifier is, that is able, how many of them it's able to get correctly classified dog as a dog. Then there's another measure which is called recall, so which is again the intersection of between these two, but divided by ground truth. Okay, so I'll say how many you are able to recall, how many able you do that, what percentage. So that is essentially true positive divided by number of ground truths. Okay, so these are the metrics: precision, recall, which is in terms of the ground truth, true positive, false positive, true negative, and all those things. So that you need to know, and it makes sense. It's very intuitive. You know. That's what ultimately you want to do. And that's the end of this lecture.